welcome everyone. So it's my pleasure to introduce our distinguished speaker for today. Cynthia Rudin is an associate professor of computer science, electrical and computer engineering and statistics at Duke University and directs the prediction analysis lab. Previously, Professor Rudin held positions at MIT, Columbia, and New York University. She holds an undergraduate degree from the University of Buffalo and a PhD of applied computational mathematics from Princeton University. She's the recipient of the 2013 and 2016 Innovative Applications and Analytics Award and an NSF Career Award. She was named as one of the top 40 under 40 by Poets and Quants in 2015 and also named by BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. So thank you for joining us today, Cynthia, and the floor is yours.
Thank you. Thank you, Sarah, for the invitation. Okay, so I've been working in interpretable machine learning for about a decade, and I have noticed kind of an alarming trend as to where the field is going. So I'm glad to get a chance to talk about this and hopefully correct some of those issues. Okay, so where do you need interpretable machine learning? You need it for high-stakes decisions or troubleshooting. You need it because things could go potentially wrong, and you want to stop that before it happens. Okay, so where do things go wrong? All right, so this is a paper that was posted recently, and they gave it an interesting name, a very appropriate name. Confounding variables can degrade generative models. But really what the paper is about is warning people not to do bad machine learning. The study was trying to use machine learning to predict health outcomes based on X-ray images. And they noticed that the machine learning method was predicting well in training, but then it didn't generalize. So what happened? Well, they noticed eventually that the algorithm was picking up on the word portable that appeared on some of the training images. And now it turns out that there were two types of images in the training set. There were those taken with a portable X-ray machine and those taken with a regular X-ray machine. So why would the machine learning algorithm pick up on the word portable? It's because the people who were getting the portable X-ray images were those patients that were so sick that they couldn't make it to the regular X-ray images, to get the regular X-rays. So if you're trying to predict who is going to have poor health outcomes, looking at the word portable is a great way to do it, even though it has nothing to do with the medical content of the actual image. So it's kind of obvious that a neural network would pick up on that. Now, if they actually used a machine learning algorithm that was actually interpretable, that they understood, they wouldn't have had to discover this issue, and this kind of thing would never have happened, and they wouldn't have had to go to the trouble of figuring it out and writing a paper about it. So this is what happens when you try to use a black box machine learning method for medical images. And by the way, this confounding issue happens in every single medical data set, every single one of them. Okay, so what about other domains? Okay, so this is a case, a New York Times article about a man called Glenn Rodriguez, who was imprisoned at a very young age for something he did as a teenager. And he was in prison for something like 17 years. He was a model prisoner. He went up for parole, and the parole board denied his parole. And he couldn't figure out why, and it turns out that someone had incorrectly entered a piece of information about him into a proprietary scoring system called Compass it's used throughout the US justice system. Somebody entered a number wrong. And this Compass model is used to predict whether someone will commit a crime in the future. Now, at the parole board hearing, they just denied his parole, and there was nothing he could do to fight it because he didn't know about the mistake in the data entry until after the parole hearing, where he compared his piece of paper to someone else's piece of paper. And the model had 137 factors in it, so it was really hard to spot this error in one of the factors. Now, while I was preparing this lecture, I got an email from someone who had almost the same story as Glenn Rodriguez, warning me that California is going to be using a black box model for bail decisions. That's what his email was about. And so I wrote an email to say, thank you for telling me about that. And he said, I didn't want to put his name because I wasn't sure if he wanted that announced, but he wrote that this exact thing happened to him as well. Okay, so this is real. This is a case where they didn't use a black box. This is a case where someone was granted bail based on a typographical error in a actually very transparent model. This guy, he was released on bail and he committed a murder before his hearing. Now, in this case, we were able to detect exactly what happened. And so the question is, if this could happen with a transparent model with only a few factors, how often has it happened with black box models? And we'll never know the answer to that question. Okay, it's much harder to troubleshoot 137 factors than it is 7 factors. Okay, this is an obvious one. I don't need to explain that. I got interested in this because of power grid reliability. I was working with the power company in New York, and our goal was to predict serious events like fires and explosions on the New York City power grid. We had data about every cable that went underground under all of these manholes. And our goal was to predict events like that, fires and explosions. And I noticed that all the machine learning methods were performing the same. It didn't matter what I did. They were all performing the same. And I was getting only about 1% difference, okay, between the algorithms. And then at one point, I went to a very transparent model, very simple model. And I showed the power company that model. And I said, look, it's using this factor. What do you think about that? And they said, there's something wrong with your model. And it turned out there was something wrong with the data. It was a confounding factor, similar to the medical example that I showed you. Once we fixed that, once we realized that having these interpretable models and having the domain experts work with us on these, we were getting these leaps in performance rather than being kind of stuck with this 1% error. So that's a case where interpretability and accuracy trade off in the opposite direction, right? Usually you think that you have to trade off interpretability to get more accuracy. But in this case, the interpretability got us more accuracy. Okay, so all of these things are happening right now, and we've been trying to figure out how to deal with this problem. And so what I've been trying to do since then is to produce tools that people can use instead of the black boxes. I don't want to explain black boxes. I want to create interpretable models in the first place. So the first thing I'm going to start with is optimal decision trees. So why in the world would I tell an audience about decision trees when most of you are only interested in deep learning? Well, for the vast majority of real problems I've encountered, as I mentioned, for structured data with meaningful covariates, it does not matter which machine learning method you use. They all tend to perform almost exactly the same. Okay, this is for structured data with meaningful covariates. You might need to do some feature engineering or discretization or something, but after you do that, they all tend to perform the same. And this is why a lot of machine learning in the last few years have been working on problems like computer vision, because those are the only problems where deep learning is beating logistic regression, So anyway, but optimizing for interpretability is much harder than optimizing for accuracy, right? Because you actually need to add in a bunch of extra constraints to your model. It has to be accurate and interpretable. So it's got to be two sets of constraints. And now decision trees are being essentially ignored. So sometimes people tell me that decision trees don't work as well as other methods. But, come on, what are they trying to compare CART to deep learning? I mean, you're comparing an algorithm that was designed in 1984 to one that's designed in 2018. So what you're comparing there is 1984 to 2018, not decision trees versus deep learning. That's not really fair. So I want to try and compare 2018 algorithm to 2018. So I will introduce an algorithm called corals for decision trees. Okay, so it's a systems and machine learning kind of co-design approach to optimal decision trees. We want sparse, accurate trees. This is one of the oldest problems in artificial intelligence. They're NP hard to construct. With no polynomial time approximations. Of course, the alternatives have serious flaws because they're myopic, greedy, top-down algorithms that don't globally optimize anything, and so they have no guarantee of optimality. So the way that standard decision trees work is like this. So I'm going to create an algorithm for whether Stan is going to get stuck in traffic on his way home from work today. Okay, so I have all of your past data. I know in the past what the conditions were under which you left work, and I know whether you got stuck in traffic or not. And unfortunately, I didn't foresee this well enough to put Fenway Park in this decision tree, but okay, so let's just go with this. All right, so let's say that rain is a big factor. If it's raining, The rain is the most informative factor as to whether or not he will get stuck in traffic. So we'll split the data set into two pieces based on rain. If it's raining, the most informative factor is, for traffic is whether there is construction on his way back. Okay? So I split the data set again, and then I can make a prediction. If it's not raining, I'll check and see if it's rush hour. If it's rush hour, I check for construction and so on and so forth. So I'm building this tree from the top down, and I'm not globally optimizing anything. And if I chose the wrong factor at the top, too bad. Okay. I can't go back and fix it. This algorithm doesn't do that. Okay, so if I could fully optimize what all the splits are, if I could fully optimize this tree to minimize some loss function, what would that loss function be? That's an easy one. I want to try to keep the model accurate, but trade off with the size of the tree. Okay? So this is misclassification error, trading off with the size of the tree. And then this hyperparameter, if I set it to 0.01, it means I'm willing to trade off 1% error for one fewer leaf in the tree. Okay? So does everybody understand what I'd like to do here? Okay. So I want to find a tree that minimizes this function. Okay? And there is all of Stan's data up there. Okay? So I want to create a tree that's accurate and also small. And I want to minimize this over all possible trees, which means I want to minimize it over every size tree, over every possible thing I could place into the nodes of the tree, and so on. Okay, so this is a very hard problem. And it could take until the end of the universe to solve on even a modern computer with even a reasonably small data set. But I don't have that kind of time, so I'm going to do something different. Okay, so I'm going to talk about this algorithm that I mentioned called Corals. And Corals solves certifiably optimal this problem that I mentioned on the previous slide. It does rule lists, which are one-sided decision trees. Full-blown decision trees are much harder than one-sided decision trees. So I'm going to start with one-sided decision trees. One-sided decision trees are like sequences of if-then rules. They're also called decision lists. Okay, decision lists or rule lists. Okay, so Corals minimizes the objective that I had on the previous slide. And it produces models like this. Okay, so this is a model that we built from the ProPublica data set. So this is a data set of people in Broward County, Florida. And we're trying to predict whether they will be arrested within 2 years of the computation of that model. Okay? Now, this model, as you can see, is pretty small. It basically says if you're young and you're male, you'll probably be arrested. I mean, this is all conditioned on you being already in the police department and getting your score computed. Else, if you're between 21 and 23 years old and you have 2 to 3 prior offenses, you'll probably be arrested. Else, if you have more than 3 priors, you'll probably be arrested. Otherwise, predict no arrest. Okay? So this model, there are 3 special things about this model that I want to tell you. The model was built in less than 10 seconds. It was certified to optimality on this data set for the problem I mentioned on the previous slide in less than 2 minutes over the full space of models of this form, if-then rule models. It's as accurate as any other machine learning method on this data set. And it is also as accurate as the model that was used to deny Glenn Rodriguez parole. That used 137 factors that's used throughout the justice system. Okay, they're all equally accurate. That model there, and all of the other machine learning methods, and the COMPAS model. Okay, so I will tell you a little bit about the Corals algorithm, but I just want to make sure that everyone understands. I'm trying to minimize that objective over the space of all possible rule lists. And the minimizer of this looks kind of like that. Okay? Yeah?
I just want to clarify what you mean by as accurate as any other ML method.
Yeah.
So that's controversial in its own way. You compare means, sometimes completely useless. The variances.
Yeah.
So what do you mean in this case?
Yeah. So actually, I'm going to present a slide a little bit later that has sort of tenfold cross-validation accuracy computed for all the different machine learning methods. So it's out of sample computation. But also, if you compare false positive and true positive rates and false negative, all the 4 rates for both blacks and whites, they're all identical across the board. Okay, so I want to talk about how to minimize this algorithm. Minimize this objective, I'm sorry. Okay, so the first thing we started with were a whole bunch of theorems that reduce the size of the search space. Because the more we can reduce the size of the search space, the more hope we can have that we can solve this problem before the end of the universe. Okay, so let me show you what the theorems were that reduce the search space. I'm not going to do any notation, but I'll give you the intuition. So the first theorem says that if a rule support is less than 1%, then the rule can't be in an optimal rule list. Okay, so what is support? Support is just the number of observations that fall into the rule. So in other words, if a rule, if there weren't very many 18 to 20-year-olds who are male in the data set, if there were less than 1% of them in the data set, that rule would never appear in an optimal rule list. It just would never happen. It's not a popular enough condition that it would appear. So we can omit that without even looking at it. We also have a bound that is about accuracy. If you add in a rule into a rule list and it doesn't correctly classify at least 1% of the data, then it also cannot be in an optimal rule list. That rule is not good enough to warrant placing it in the optimal rule list. Yep.
So this is just binary classification? Yes.
Just binary, yeah.
Should my goal be correctly classifying half plus lambda, or really lambda? I can be right half the time just by closing my eyes and guessing randomly.
Yeah, but that won't minimize your objective, which is try to make the whole model accurate.
I guess I was just asking for theorem 2, what's the notion of sort of a non-trivial? Okay, I believe what you said on the slide.
Okay. Yeah, I'll go back and explain again.
I'll ask my question then later.
Yeah, it's hard to do this without notation. With notation, it's much easier, but I was told to keep it for a general audience, so I'll do that. Okay, so for example, if this rule, age between 21 and 23 and 2 to 3 prior offenses, if that doesn't correctly classify at least 1% of the data, then I can omit that rule, and the rule list will have a lower objective value.
Right, but I could also complement that rule and be right 99% of the time.
But that doesn't work because the rule doesn't apply. The rule doesn't apply to 99% of the people.
Are you assuming that all of them are predicted rest until the last one?
So
is that a constraint on your rule list?
Okay, anyway, sorry.
No. Let's try it again. So age between 18 to 20 and sex is male. So let's say that applies to only 2%. Let's say it applies to 1.5% of the data. Okay. So you only have 1.5% of the data that fit into that rule. And the rule classifies half of them one way and half of them the other way. You just can't get, there's no way to get above 1% of them classified correctly with that rule.
I see. So a rule has 3 possible outcomes. It's yes or no or move on.
Yeah, you got it. Yeah.
All right,
Because it's if the conditions are true, then do this. Else if, and then like that. Yeah. Sorry, it takes people a little while to get used to that, but thank you for thinking about it. Okay, so, and then rule lists can't be too long. We have this nice, it's called a one-step look-ahead bound that actually computationally is really helpful. And it says that if the rule list is not long enough, is not accurate enough with respect to how long it is, then you can't get to the optimal rule list by adding anything to it. So it means, you have a bunch of rules in there that are sort of almost accurate enough, and then if you try to add one more to it, it's going to be not optimal. Okay, the equivalent points bound is a little hard to describe without notation, but if you have 2 identical twins, so people who have the same criminal history, same age, same everything, and one of them was arrested and one of them wasn't, there's no way you can classify both of them correctly. Just can't happen. And so when we take that into account, computing our lower bound on the objective, it actually really helps us get a tighter lower bound. The permutation bound is also really important. if you have two rule lists and you permute two of the rules, like you literally flip which one gets considered first, and it becomes less accurate, there's no way the less accurate one is going to be extended to form an optimal rule list. It just can't happen. So what we have to do is every time we see a new set of rules that we've never seen before, we have to see whether we've seen those same set of rules in a different permutation before that was better. So we actually have to keep track of all the best permutations of all sets of rules we've seen in the past. And we have a special data structure that keeps track of that called a symmetry-aware map. Okay, we also use a lot of computer system techniques. We have a custom bit vector library for evaluating the rule list quickly, computational reuse, which means if we've already computed part of the rule list evaluation, then we don't need to redo it. And then a priority queue for telling us where to search in this giant space of possible decision lists. So the way the algorithm works is that it searches around in the space, and then it uses these theorems to chop off these big pieces of the search space and keep searching very quickly, and then chop, 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 chop until it gets to the provably optimal solution. All right, so here's the full outline of the algorithm. There's the data structures are a prefix tree that keep track of every sort of, we're going to build these trees from the top down. So it keeps track of all of the intermediate computations, the trees we want to look at and where we've gotten to. We have the symmetry-aware map that keeps track of the optimal permutation for each set of rules. And then we have a queue that tells us what we're going to do in what order. We use a data mining algorithm to get all of the possible rules that have support above lambda, because we've now proven that you only need rules with sufficient support. So those go into a big pile. And these data mining algorithms are fast. They've been built over 20 years by the data mining community. So those are fast. So you start with this giant pile of rules, basically, and now you have to assemble them into these rule lists. So you take all the rules, and pretend they're rule lists of size 1, and plop them into the queue. And while the queue is not empty, you take the current prefix from the front of the queue, and then add one more rule to it. So now you have rule lists of size 2. And then you check all of these things. You check all of these theorems. Is this thing too long? Is the new rule that I added accurate enough? Is it accurate enough for how long it is? And then you use the equivalent points bound to get a better lower bound for the objective. And then we have symmetry-aware pruning, which says, have I seen this set of rules before in a better permutation than the one that I currently have? Now, if the lower bound on the objective is higher than the current best, that proves the prefix is no good. Otherwise, like this means there's no way you could extend this prefix to get a provably optimal one. Otherwise, then the prefix could be extended to be the best rule list, and you add it into the queue. Okay, now if you happen to have found an objective value that's better than the best one you've seen so far, it means you have the best rule list you've seen, you update it, and you store the new rule list as the best one I've seen so far. And that's it, and the output is the optimal rule list with a certificate of optimality, which is that the queue is empty. Because if the queue is empty, it means you've either traversed the entire space or you have eliminated it through these theorems. Okay, so this is the plot that I promised you earlier about the accuracy of all the different machine learning methods. This is tenfold cross-validation, which is why there are many different values for each algorithm. So this is general linear models, support vector machines with Gaussian kernels, boosted decision trees, CART, random forests, and so on. And the colors don't mean anything. That's just the folds of the tenfolds. And so again, this is all out of sample, because you've reserved one part of the sample to test on and train on the other part. And so what you can see here is that maybe CART's a little bit less accurate than the other ones, but all the other ones perform approximately the same. Compass is the one that's used in the justice system, okay? Throughout the justice system, the one with 137 factors. And then Corals is here. But of course, the difference between Corals and all the other methods is that Corals is producing models that look like this. It produces pretty much the same model on all 10 folds of the cross-validation. Yeah?
Clarification on your rule complexity. Like in this example, you had
Yeah.
It'll probably be a really large subset.
Yeah, that's right. So okay. So that's a really good question. It's a very complicated answer, unfortunately, but I'll try to keep it short. So for this particular application, we just chose a whole bunch of bins and threw them in, okay, because we needed to use categorical variables. We have a theorem that tells us that if you have rules that are too close to each other, that you provably can't use both of them. The problem is putting that bound into the algorithm actually made our computation time worse because we were checking it too often. So we have to figure out exactly how to get. We actually wrote that as like the major challenge in the algorithm is to figure out how to do this. So for this, we simply chose a whole bunch of bins and threw them in. And in practice, it didn't really harm us to do that. That's the truth. But ideally, we would like to sort of have every possible bin and then have the algorithm sort of, be able to handle the fact that these bins are very similar to each other. Yeah.
The outputs I've seen from Compass also give you they claim to be calibrated predictions of probabilities as opposed to just classifications.
Mm-hmm.
I would imagine that one could modify. I mean, with decision trees, you could do the same thing and train for some proper scoring rule instead of
Yeah.
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 Classification error.
Mm-hmm.
And I was wondering if the kinds of the theorems the kind of elimination theorems you have, if they apply to those types of settings.
Yeah. So luckily, we tried to solve that problem first. So actually, corals is derived from a method called scalable Bayesian rule lists, and Bayesian rule list does produce probabilistic outputs. The problem with, and we did use theorems similar to the ones that we derived for corals. The problem with those is that with corals, everything is discrete, so you can prove the answer to certifiable optimality. Whereas with the Bayesian methods, there's exponentials in everything, and so it's much harder to prove optimality. We could get, like, actually, come to think of it, here, I have performance from scalable Bayesian rule lists right there. So if you do the thresholding, scalable Bayesian rule list performs the same as these others, but that one produces the probabilistic outputs. Yeah, but it doesn't have the certifiable optimality on the objective that the corals does. Okay, so a note about corals is that if Leo Breiman had invented corals, he probably wouldn't have wanted to use it because it would have taken him 4 years to prove optimality of the rule lists, whereas for us it only takes 2 minutes. So I think we have to think about this algorithm in the context of the computational power that we actually have now. Okay, so and the code publicly available, and we even have on the website the data set loaded up onto the website, so you can just click go, and it'll actually start running the data set, the data set on there.
Actually, an unrelated question. To go back to your performance.
So the Compass system is actually being used?
Oh, it's used throughout the justice system. Yeah.
And its performance is around 67% accuracy? So how can that be justified? It seems wildly inaccurate.
The problem is that judges are even more inaccurate. Okay, so the judge is supposed to take all of the information about the case, digest it all, and make a decision, right? So this, Compass at least gives them some sort of baseline that is, calibrated and supposedly useful. Like it's at least not based on the way the person looks. You know what I'm saying? It's based on their criminal history, their age, and other things like that. It's mostly based on age, to be honest. And then the judge is supposed to combine that with the other information that they know and make a decision, like should I grant this person bail or parole, something like that. So these risk scores do provide that sort of something quantitative about the risk, right? It's just that's that's what it is. It's better than the alternative, which is the judge trying to guess it from looking at the person, looking at their race, and looking at what they're wearing, and looking at what they think the age of the person is, and so on. Okay. So we've been actually trying to extend this to full-blown decision trees because, you know, decision lists are, it's great to be able to do it for decision lists, but, you know, the big goal was really full-blown trees. Binary split decision trees. So we thought, well, now we've actually gotten it to work for lists. Maybe we could try it for trees. And we've been working on this for about a year, and we've actually sort of got it to work. We extended all of the bounds from corals to trees. And what I'm showing you are the very first results from that algorithm. So it's actually producing certifiably optimal trees for the Florida data set. And we're just about in the process of writing that up. So that's where we've gotten to so far with this project. Okay, thus optimal sparse decision trees and lists are possible. Now, I just want to make a note about the usage that, you know, you want to use decision trees when you have meaningful features in the first place. These are the kind of data that doesn't really matter which algorithm you use, where they all perform the same. Obviously, you know, decision trees make no sense for computer vision because, you know, you don't want to create conditions on the pixel values. That doesn't make any sense. So we need a different notion of interpretability for computer vision. So I want to make that clear. Okay, so let me then talk about what you would do for computer vision. So this is current work. We're still kind of working on how to do it, but we wanted to design a neural network for computer vision that's the same accuracy as any other neural network, but that has some constraints that make it more interpretable. And I'm not a computer vision person, but you know, I think we got a lot of sort of flack for saying, well, okay, you know, you can add these extra constraints and keep the model interpretable. And people were saying, well, you can't always do that. And I was thinking, well, maybe we can. So let's try to do it. So what we're not trying to do is explain black boxes. Black boxes can be misleading, and it's not clear to me that you actually need black boxes at all. I've worked on like 50 applications or something. I've never needed a black box. Because, you know, if you have an explanation method that's right 90% of the time, it's wrong 10% of the time. So in that case, you can't trust the explanation, and therefore you can't trust the black box. So I know a lot of people really like these explanations, but there's all kinds of weird issues with them. I actually wrote a paper for the CRACKed workshop, the Critiquing Trends in Machine Learning workshop this year. And I wrote about why we should care about interpretable models rather than explainable models. So for example, a lot of people really like saliency maps, and that sort of, you know, try to show where the neural network is looking within the image. And that tells you where the network is looking, which is great. But it doesn't tell you what the network is doing with the pixels it's actually looking at. So for instance, I have no idea why that's classified as cat. Okay, so let's talk about what kind of notion of interpretability I might actually want. So how do humans tell each other why they classified something a certain way? So let's talk about difficult visual classification tasks. So bird watching, bird identification, that's a kind of a hard classification task. And what people tend to do is they put markings all over the image, and they tell you, well, this looks like this thing this looks like this. This is the prototypical thing of what that type of sparrow looks like. You know. This is from a bird watching website. But people do this also for architecture. They do it a lot for medical screening and diagnosis. They look at past cases and they say, this looks like that patient's thing. This looks like that thing I've seen before. This is a prototypical, you know, whatever. So they not only tell you what part of the image to look at, they tell you why. So they'll say, you know, that part of this image looks like, you know, this part of this image, this part of that image looks like a prototypical you know, head of a clay-colored sparrow. And this part of the image, you know, the chest of this bird looks like a prototypical chest of clay-colored sparrow. And the feathers look like, you know, this looks like that thing I've seen before, and this looks like that thing I've seen before. Okay, so the difference between these is that the explanations here are visual, and the explanations here might be words or might be visual or something else. But of course, the one on the left was automatically generated by our algorithm, and then the one on the right is from the birdwatching website. Okay, and so since our network says this, this part of the image looks like that thing I've seen before, we decided to call the network "This looks like that." So it's called "This looks like that." That's what it's called. Okay, so this looks like that. It's a case-based reasoning method. It's not k-nearest neighbors. I didn't want to do k-nearest neighbors because it didn't make sense to me. I didn't think k-nearest neighbors was interpretable. I don't want to compare the whole bird to a whole other bird. I wanted to compare parts of the bird to parts of prototypical birds of that class. So it's more like k-nearest parts of prototypical cases. Now, the way the network architecture works is that you take your favorite black box and you add an extra layer on the end to do this prototype computation. Now, the prototype computation it's much harder. The tricks that have been developed for standard computer vision have not been developed for this prototype network yet. But we have not lost any accuracy to solve some of these very hard classification tasks. Okay, so even in this case of deep learning for computer vision, we still think you can add interpretability constraints to make the model somewhat interpretable and so that it's not a black box. Okay, so the objective of the algorithm forces it to perform k-nearest parts of prototypical cases and encourages the latent space to be clustery so that the neighbors actually make sense and there's clusters for different parts. Okay, so how would we classify this image? So I'm going to blow up the image, so just keep that image in your head and I'll show you kind of what it does. Okay, so there's the image there. So why is this bird classified as a Lincoln sparrow? All right, so here's the evidence for the bird being a Lincoln sparrow. So it's looking at this is showing you this is showing you where on this image the network is actually using to compute similarities. So it's saying the feathers of this guy over here look like this guy. This is a prototypical, one of the prototypes for Lincoln sparrow. And it's saying the face of this bird looks like this prototypical Lincoln sparrow. And then this part of the bird over here looks like, this is again kind of zooming in on the pattern of the feathers. And then each of these prototypes gets its weight. Each of them has a special weight to that class. Okay, so this is the similarity between this bird, and this is how similar the network thinks this part of the bird is to this guy. And then this thing is how important the prototype is. So when you multiply them all together, you get the points for that particular class. And you add them all up, and you get the total points for Lincoln sparrow. Okay, so that gives you, so you take the image. Different parts of the image are more similar than others to these prototypes. The prototypes are each weighted. Multiply them together, and you get the total number of points. Okay. So, and then we can look at the this is the class it actually is. It actually got this image correct. But if it didn't get it correct, it would have chosen this class, which is the Henslow sparrow class. And then here, what it's really kind of zooming in on are the feathers, the pattern in the feathers. It thinks that those feathers look like the feathers from these Henslow sparrows. Okay, but it doesn't get as many points for the Henslow sparrow class as the Lincoln sparrow class, and so that's why it classified it as a Lincoln sparrow. Okay, so I'll show you another one. This is a western meadowlark, and you can see where it's activating. So here on the back of the bird, it's looking like the back of this bird. The belly here, and then this is looks like the kind of darker part of the belly over here. And there's the total number of points again. And then this is evidence for it being a grasshopper sparrow. And then here again, it's looking at the pattern of the feathers and thinking that that's what's making it similar to that class. But again, this is much less similar to this one, which is the correct answer. Okay, so let's see where it goes wrong. So this one it got wrong. So it said that it was a prothonotary warbler instead of a Wilson warbler. here's the evidence for it being that prothonotary warbler. And you can see it's really kind of looking at the back of like the feathers, the dark feathers of that warbler and the face. Whereas the correct class, it didn't get it right, because even though it was looking kind of, well, it was looking at the face, the belly, and just this like the chest area, but it just didn't quite get enough points to classify it correctly. So you can see kind of where it went wrong. And this is another case where it went wrong. And here it really thought the feathers of this bird looked like this other class. Whereas for the correct class, again, it just didn't quite get as many points looking at the chest area, which would have been the correct way to sort of identify the difference between this bird and that bird. Okay. So we've been working on trying to apply this to mammography data, which is more obviously a higher stakes decision, and we're hoping that we can sort of explain to patients why their image was classified as malignant or benign. So this is a case where it's malignant, and here are the prototypes that are nearby, the kind of prototypical malignant cases, and then here are the benign cases where it's showing like tissue that's similar to the tissue, the breast tissue over here, except sort of without the things that make it malignant. So it hopefully will help explain to the patient why their tumor is malignant. But we're still working on the data processing for this data set. I don't think we've quite got it quite right. You can tell whether you've got the data processing right because you can look at the output of the interpretable model, and if you can't interpret it quite right, you know that there's something wrong, which is very helpful for troubleshooting.
Brings up a question. Have you looked at all at sort of whom the sort of question of interpretable to whom?
Yeah.
So, interpretable to, you mentioned providing an interpretation for patients, but that might be very different from providing an interpretation to a physician.
Yeah, so
Right.
that's
Has that
that's a
come
good
up at
question.
all?
Of course it's come up. every choice that you make of interpretability or accuracy, how you measure performance is always domain dependent. And so it's always about, who your consumer is or how useful it is. So yeah, that's the critical thing here. Yeah, absolutely. We haven't gotten far enough yet that we've felt comfortable engaging a mammographer yet, but we have our hands stretched out to try and get somebody to help us out with that. Yeah. Yeah.
In this method, you're not incorporating the spatial constraints on the pulse of the curve.
Spatial constraints.
We're talking about recognizing multiple parts.
Yes.
To do your nearest neighbors, right?
Sure.
Those parts in a particular object must be in a particular orientation to each other in order to satisfy the constraint. This is that object. It sounds like you're just taking the product of the matches, taking conjunction of the matches. I got those K out of N matches without considering how they are oriented to each other. You're matching some images, right?
Yeah.
Well, that's important that eyes are above the tail.
Oh, yeah. Yeah, so this network doesn't do that. Yeah, this network doesn't do that. You could make it do that, but we didn't do that. Yeah, it's literally just doing this nearest neighbor thing, and it's not looking at where the parts of the birds are. That's right. Yeah? Sorry, can I get this one first? Can I answer this one first? Okay.
So how is the similarity score computed? How is
so
the
that's-
similarity score computed?
Yeah, so it's actually the Euclidean distance in the latent space. Yep.
Just small question about spatial distribution. Images on the left, you providing examples for overlapping cases. Like how much sense does it make? So you're finding the closest images for the same patches.
Yeah. Sorry?
Like usually in the case of bird, you're providing like this head is similar to this canonical representation. This tail is similar to this canonical representation. But in this example, you simply providing these dots similar to these dots. And these dots again similar to these dots. So like, what's the point?
Yeah, well, what's the point? Okay, so I think maybe I won't answer that question the way you wanted me to, but I mean, the idea is that you're supposed to. So, like I said, we're not advanced enough. Otherwise, I would have focused on this on this example. But we're not advanced enough to be able to do it quite yet. But the idea is you're supposed to look at that case and see prototypical similar cases. So, for instance, if there's like a strand where there's like a tumor growing along this strand of tissue, then hopefully you'll see that there are prototypical cases where that also happens. You know, here it's like looks like microcalcification. So you're seeing prototypical examples of different kinds of microcalcifications. Okay, so yeah. So the network chooses the prototypes. They're parts of the training examples. That's part of the training process.
Would this work for a small set, a small data sets? Because I'm assuming like maybe you don't have a lot of images of, the.
Yeah, so this is a publicly available data set, and it's not huge. So we have to do a lot of like augmentation of the data, which is kind of annoying. It does work better when you have a larger data set. The birds also is so annoying because you only have like a small number of, you have a huge number of birds, but like images of birds, but there's a small number for each class. So it's really hard to actually discriminate between them. So you have to do a lot of data augmentation.
So is it like kind of like the accuracy you get, is it dependent on the number of classes or number of samples in each class somehow?
Yeah, it depends on the number of samples in each class because you've got to be able to distinguish one class from the next. So it does make it harder when you don't have that many.
And I had a question about class connection. How do you actually compute that one?
Yeah, it's all computed as part of the training process of the network. Yeah, I think I'm gonna move on to the next section so that I can finish, but I'm happy to take questions a little bit after. Okay, so thus we haven't found to sacrifice in accuracy to do a form of case-based reasoning. The explanations are completely faithful to what the network actually computes. It's not a post hoc method. And I have still yet to find an application where I actually needed a black box. I'm not claiming that none exists, but I claim that I have not found one, and I've worked on many, many different problems. Okay, so it makes you puzzle over why people are using black box models for high-stakes decisions. And it's particularly bad, like in the US justice system, where things have gone very, very wrong with using black box models, as I mentioned. So I want to take a step back and ask historically about what people considered to be an interpretable model. So how did humans design predictive models when they didn't know machine learning? Like they can design the model however they want because they don't have data. So they can design whatever they want. And to be honest, what they've been designing for the past 100 years are scoring systems, which are sparse linear models with integer coefficients. So this is probably the most widely used predictive model in medicine. It's called the CHADS2 score. It's a sparse linear model with integer coefficients, which are these point scores. And then when you add up the points, it translates into your risk of stroke. Okay, so that's our scoring system. Okay, so this has been done for the past 100 years. This one's from 1928. This is, again, a scoring system for successor parole. And you can see people get points for being like a drunkard or a gangster or a recent immigrant, a ne'er-do-well, or a mean citizen. So yeah, this is a more recent version of that. This is the Pennsylvania Commission on Sentencing score from 2013. It's still the same kinds of models in criminology. People like these models. It's easy to understand the contribution of each of the factors. There's tons of these things in medicine, hundreds of them. So they're all of the same form, and we thought, okay, why don't we try to actually create these things from data? So we designed an optimization problem to do it. Here, this is called risk slim. It's logistic loss traded off with model size. And then the coefficients being in this set L means that they are like small integer coefficients. Okay, so between maybe -10 and 10. And you can add other constraints onto those if you want, like false positive rate above a certain value, below a certain value, or something like that. Okay, so the way cutting planes usually work is that you have this sort of convex function you want to minimize, and you start somewhere, and you compute and you know it's non-negative, you know it's convex. For us, this is the logistic loss. And the algorithm starts by calculating the objective and the gradient. And then it generates a cut using that gradient that it calculated. And it minimizes the blue surrogate, which is going to be a piecewise linear function. In this case, it happens to know the objective is non-negative, so it picks that spot and then keeps computing objective values and gradients and adding the new cuts. And again, it's supposed to minimize the surrogate, but the blue surrogate, again, it's non-negative, so it goes there and keeps going. Again, you can see this is a linear program here. It finds that point, adds the cut, and then it finds out that, lo and behold, the minimum of the surrogate is the minimum of the objective. And when this happens, the algorithm knows it's found the minimizer of the objective because the minimizer of the surrogate equals the minimizer of the objective function. But something goes wrong when you're creating models with integer coefficients. So let's show where that happens. So let's say that you're here in the computation. So you created, you iteratively constructed that surrogate there, and you can see the solution to this picture, the solution to this minimization problem in the picture is a linear program. So it finds that point right there. And then in the actual problem we're trying to solve, though, all the coefficients have to be integers in the optimal solution. So that might not be the optimal solution because it might not be integer. Like we might actually want a solution that's over there. Okay, because all the solutions have to be integers. Okay, so the feasible region is the integer lattice. And so hopefully you'll realize that the problem that I put on the board a few minutes ago, the optimization problem, is a mixed integer nonlinear program that is very, very difficult to solve. And if you send it into a generic solver, you'll never solve it. Okay. So if you try to solve this problem and try to find the minimizer in the feasible region, you're solving a mixed integer program. That's bad. So what happens is, when you find the point, you have to find the point on the lattice that minimizes the objective, and you need to solve the MIP to optimality at each iteration, because otherwise you have no idea whether you've solved the problem. Okay, so and still every iteration you're adding a cut. So as you add more and more cuts, the MIPs that you have to solve to optimality grow bigger and bigger, and then forget it. You're done. So no matter how big or small the problem is, after you add 200 cuts, the problem becomes difficult and it totally stalls. So this is after you have about 70 cuts, the number of seconds per iteration to solve the MIP just blows up. 10,000 seconds. That's it. You turn it off. Done. You can't solve it. And then the optimality gap is supposed to go to 0, but it stays at 100% because you just can't solve it. So we designed a new cutting plane method to do it. And what the method does is instead of solving the MIP, so instead of finding the minimum on the feasible region, it actually solves the linear program. It actually solves this thing over here. And OK, that's much easier to solve. So what does it do with that solution? Well, it says that I know there's no feasible points in here. So I'm going to divide the space into two pieces, the left and the right. And I'm going to deal with each piece separately. OK, so it does that. And then it solves the linear program in each piece. And then here, from there, if it happens to land on an integer solution like here, it can add a cut. And otherwise, it can't. And so here, we've actually found the optimal solution very, very quickly. But in reality, you would have to add several cuts to find the optimal solution. OK, so it continues like this by either subdividing the space or by adding a cut at each iteration. And here, when you do this, you can run it for as many iterations as you like. And the time to solve the linear program never gets too high. It never gets above 100 seconds. And then the optimality gap goes nicely down to 0. And it never stalls. And it's super happy. Another nice thing about this is that since it's a cutting plane method, the solver never sees the data. So you can just scale it up to 10 million observations, and it never has any problem because the solver only sees the cuts. It never sees the data. So the time spent on the solver stays constant, and the time grows linearly with the amount of data because the data is only used to compute the objective and the gradients. So it's really, really nice. We've worked on a lot of applications with this, including sleep apnea and seizure prediction and stuff like that. But I'm going to show you the results of our ADHD scoring system. So this is for diagnosing ADHD in adults. And I'll leave it up there for a few minutes in case you want to diagnose yourself or screen yourself or whatever for ADHD. But essentially, it replaces a model. Like they actually changed the criteria for what constitutes ADHD, and the new criteria is more lenient. So we were working with a collaborator who he was like, oh no, I got to redo my scoring system, and he was trying to do logistic regression and rounding it and trying to eliminate features. It was very difficult for him, and he found this tool, and he was like, oh, I can just, this is great. It does all the feature, choice of features and puts the scores in there and everything. I don't have to fiddle with it. Okay. Okay, great. So just to conclude a little bit, I got a couple more slides. So I showed you 3 methods: a systems and machine learning approach to hard decision tree problems, cutting planes and branching bound for scoring systems, and then neural networks and case-based reasoning for computer vision. I have a concrete proposal, which is that I think we should be governing interpretability before explainability. And we should for high-stakes decisions, we should force people to resort to a black box only when no interpretable model is available. No interpretable models exist. So if you sell somebody this is a credit scoring model, it's a black box, then if there's an interpretable model that's just as accurate, this is false advertising. Okay, so I wanted to end with something kind of fun, which is that no more of the serious stuff. So I taught a class last semester for Duke. It's the first time the class was offered. It was called Data Science Competition. It was a new course at Duke, and it had only undergraduates, mostly sophomores and juniors in the class. And they entered 2 competitions, and they won 2 competitions. So I want to show you a little bit about what they were doing. So the first competition they won was a single image super resolution, and the second one was an automatic poetry generation competition. So I want to show you what they were doing. It's pretty fun. Okay, so this is an input image that the super resolution team started with. So they started with this, and I'm going to show you what the output of the algorithm is. This is the input. Okay. This is the output of the algorithm. Okay. Okay. So watch these leaves really carefully. I'll show you the real image that generated the low resolution image on the previous slide. So watch those leaves. Okay. So that's the real image that they started. The high definition one that they were trying to replicate. Okay. So again, this is the starting image, their algorithm's result, and the ground truth. Okay. Here's another example. This is the starting image, algorithm's result, ground truth. Okay. So take a look at the bottom of that brown plate there. Okay. Algorithm's result, ground truth. Okay. Okay. Now the poetry, they did win, but the poetry's not very good. So it at least gave us, it was a good learning experience. We have a bunch of ideas of how we can improve the poetry. I'll let you read it. Yeah, that's the last one. Yeah. We got some work to do. It's not that bad. I don't know. All right.
It's fun that it learned that, using character break mythology in the title is a sign.
Oh, the title I put on there, that was just me. The poem is what was generated by the method. Yeah. All right, thank you.
In the bird example, in one of the misclassified birds had a red crown, but none of the prototypes you showed had that in there. And you started to talk about this a minute ago, but I was thinking about sufficiency of your training set, and particularly for interpretable models, one of the things you might want them to be able to interpret is there is insufficient evidence to draw a conclusion. So I'm just wondering what you've thought about in terms of knowing when you have a sufficient training set given these other constraints of interpretability as opposed to accuracy, and if you've put thought into just rejecting a conclusion when it seems unwarranted.
Yeah, that's a really good thing. We're actually working on something very similar to that. We're working on these these cases where you know that it's, let me see if I can get back there. Oh, I don't know if I can. But we're working on these cases where you know it's like a tern. You don't know if it's an Arctic tern or this tern or that, like, you don't know which of the subclasses that it actually is. So that's a problem we're working on. If scores of two classes are similar to each other, it means that the neural network is having a hard time figuring out which of the two classes is the one that it should choose. So you actually have some measure of the confidence just looking at the total score for each class. So yeah, you can definitely see that. Mm-hmm. Okay, let me get to her.
Do you have any comments on what's considered interpretable to machine versus what's considered interpretable to human? Are they always the same, or does it have to be the same?
I'm not a machine, so I don't really know what's interpretable machines. I sort of feel like I almost know what's interpretable to humans, but it really is very domain dependent. Sometimes people like sparse models, and sometimes they don't. So I'm not sure. Yeah.
So many questions to ask you, but I guess time is short. So so this is back about birds. So one of the questions one could ask is, so let's say it made a mistake. Is it because there is not enough data? Is it what would I do to improve the algorithm?
Yeah. Yeah, that's a really good question. So there's a bunch of things you can do to improve it. If you notice that it's, you can tell sometimes when it doesn't have enough data. So for instance, if it's not looking at the right parts of the birds to make the conclusion, you know it doesn't have enough data. And sometimes you can augment the data set to try to create that extra data you need to get it to pay attention to that part of the bird that you want it to. Yeah, I think that's the whole idea, is being able to see into how it's doing its classifications. You know kind of what it's thinking, and you know how to change it. This is how we know that there's something wrong with the processing of our mammographic mass data. That we know that the network's not doing what we think it should do, and so we need to improve our data processing. Like recently we found out that, that we think our region of interest is too small. So we're zooming too far into the tumors, we're not getting the calcifications, we're not getting context of the calcification. And so we need to zoom out on it. And that's something we learned from, or humans learned from looking at the output of the model. Yeah.
Hey, I had a couple of last minute questions. So one, there's been, in the context of the first part of the talk, there's been a lot of work in the last, 20 years on sort of various types of discrete optimization, stat solvers and kind of heuristic methods for solving things that, again, weren't around in the early 80s when decision trees and lists were first developed. So are there contexts where you can sort of just leverage all of that existing work rather than having to custom design methods as you were doing there?
So I actually wrote a paper published in Mathematical Programming C this year with a MIP solver for the decision list problem. It's really, really slow. Also, there's a company that was founded based on a MIP method for decision trees. And they published a paper on their work. They didn't release code, but they published a paper on it. And there's a tree in there that's clearly suboptimal, because they clearly were not able to solve the problem to optimality. We're working right now on doing a comparison with a SAT solver approach to decision trees. I thought it was a really interesting approach, and we're working now on trying to sort of compare our decision tree method to this SAT method by Verwer and Zhang. I can give you the reference later if you want. It's a really neat approach.
So my other question was just to come back to the question about scores rather than decisions. So it's a sort of a meta question. Do you think if in these kind of high stakes contexts like recidivism and if you were training models to provide good calibrated scores as opposed to a hard decision, would it change? Is your intuition that there are lots of cases where it would change the kind of model one would want to produce? Like, let's say, just even if you stick to decision lists, right? Yeah. And then the second question that goes with that is, like, actually, if we think of these models as providing advice to a human decision maker, are they doing? One way is to produce a good decision list, right? And give the decision list as together as the advice. But maybe there are other formats that make sense. And I don't know if you've given that any thought.
I've given it a lot of thought. I don't have time to reveal all the thoughts that I have on it, but the one thing I can say about decision lists is that we have so we have all this decision list stuff that produces calibrated probabilities. And we've even tried to constrain the probabilities so that they decrease as you go down the list, so that the most vulnerable groups of patients are actually on the top. And we thought that would be more useful to groups of doctors and patients. And I've spoken to groups of doctors, and they were like, oh yeah, this is what we're looking for. We want these groups that are prioritized. So adding that extra set of constraints in there actually does help make it kind of more useful to them. But I would imagine that there are other types of constraints that you could add in to make these models more interpretable or more useful. If you think of some, let me know. Yeah, I think monotonicity constraints is, what I'm saying is monotonicity constraints are a good way to add interpretability in general, and there are other ways to do it too. Yeah, okay, great, thank you.
I'm Simon.
Hi,
Nice to meet you. Can I add one piece of wisdom to your story? Just coming from old age experience, okay? So I agree with you, as you can imagine, right?